Hello Chem 1A, this is Chapter 6, Lecture Video 4, and we're going to continue talking about the Q is equal to mc delta T equation and some of the ways we can use it in a process known as calorimetry. Alright, so one of the things that we can relate is the Q of the system versus the Q of the surroundings. Now, we can use the relationship between these two things to calculate a substance's heat capacity that we don't know. For instance, if I drop a piece of hot metal, in this case it's iron, right? I have a piece of 55-gram iron, and I know its temperature because I can measure it, and I drop it into this water, which I know the temperature of, and I know the mass of, right? Like we talked about, eventually these two will reach what we call thermal equilibrium, right? And so at some point in the future, they both reach the same temperature. The water increases in temperature and the metal decreases in temperature. We know the specific heat of water, right? C for H2O liquid is 4.184 joules over grams degrees C. And so I can actually use the amount of energy that the water absorbed to calculate what the specific heat of the metal is. And this is all through the assumption, which is not a bad assumption and it's a totally accurate one, that all of the energy that the water absorbed came from my metal. So in other words, the amount of energy that water gained is equal to the amount of energy that my metal lost. So Q of water would be equal to negative Q of the metal. Now this relationship can be applied to system and surroundings as well, because as we learned in a previous lecture video, the energy the system absorbs had to have come from the surroundings. The energy the surroundings absorbed had to have come from the system. So we can relate these two Q values and calculate valuable information from it, like the specific heat of iron if we wanted to. So let's do an example of that process or that calculation. So again, like we said, negative Q metal is equal to Q water, or we could actually have written this exactly the opposite. It wouldn't matter. Negative Q water is equal to Q metal. It honestly doesn't matter which side of the equals sign that the negative is on. It's just that one side has to be times -1 of the other. So effectively what we can do is we can do 2Q is equal to mc delta T problems, set them equal to each other, but make one of them negative, in this case either the water or the metal. So I have a 45-gram piece of copper metal, and it's at 100 degrees Celsius. And I'm going to place it in 250 grams of water at 25 degrees Celsius. We're told that when the system reaches thermal equilibrium, the temperature is 28.8 degrees Celsius. We're going to assume the calorimeter is perfectly insulated, and we're going to do that for pretty much every problem we do in this chapter, because if it isn't, then there's really no way to calculate our answer here. So we know a couple things, right? So for water, I do not know what Q is yet, but I do know what the mass of water is. That's 250.0 grams. I know what the initial temperature of the water is. It's 25.0 degrees Celsius. I know what the final temperature of the water is. That's 28.8 degrees Celsius, because the temperature of the water at thermal equilibrium, there we go, we're given that final temperature. I also know that the specific heat of water is 4.184. This is a value that will always be given to you if you need it. All right, probably on the equation bank. Okay, and this is specifically liquid water, and we'll talk about that in the next lecture video. Specific heats, as we talked about previously, have different values for different physical states. Okay, so if we look at all of this information, I can calculate Q of water because I know Q of water has to be equal to mc delta T. So my Q of H2O is equal to 250.0 grams times 4.184 joules grams Celsius times the T final, 28.8 minus 25 degrees Celsius. And so Q of my water has to be equal to, if I just do that, plug it in my calculator, about 3,974.8 joules. Now, we actually only know this to 4 significant figures, or actually, 2 significant figures. So technically, we would round this to 4,000 joules if this was our answer. But again, we don't round values until the very end. So we're not done. We're actually being asked for the specific heat of copper, right? Well, I know that Q of my metal, here I'm going to do this in a different color. Q of my metal, Q of my metal is something I want to know, but I also know that it is equal to negative Q of the water. So Q of the metal we actually can determine right now. That is equal to negative 3,974.8 joules. I know the mass of the metal. That's equal to 145 grams. That was given in the problem. I know the initial temperature of the metal, Ti, is equal to 100.0 degrees Celsius. And I know T final, because at thermal equilibrium, both the metal and the water have to have the same temperature. So T final is 28.8 degrees Celsius. So if I know all that, I can actually calculate C, right? So negative 3,974.8 joules is equal to 145 grams times C, whatever my specific heat is, times 28.8, my final temperature, minus 100. And we can rearrange this and solve for C. And what we get is 0.385 joules over grams times degrees Celsius. Which, I mean, technically we should round to 2 sig figs, so this would be 0.39 joules grams degrees Celsius. So this is one of the ways we can use that relationship to solve a little bit more of a difficult problem for Q is equal to MC delta T. Let's do one more, and this one's probably the most challenging so far. So we have a 325 gram sample of iron at 100 degrees Celsius. We have a 320.5 degree sample of water at 25 degrees Celsius. And we have the specific heat of water and the specific heat of iron. We want to know what the temperature is at thermal equilibrium, which basically means what we're asking for is T final. All right, now if we look at this, we have a slight issue. I cannot calculate the Q of water. I know that the mass is 320.5 grams. I know the specific heat is 1.84 joules grams Celsius. And I know T final minus 25 degrees Celsius is my delta T. But I don't have T final, so I can't calculate the Q of water. At the same time, for the metal, Q of Fe, that's equal to 324.5 grams times 0.444 joules grams Celsius times T final, again, we don't know that number, minus 100 degrees Celsius. So again, we don't know these two values yet for T final, but the nice thing about this is these two T finals are going to be equal to the same value because the systems don't reach thermal equilibrium, and that's what that means. Now what I can do is I can say, hey, Q of H2O is equal to negative Q of Fe. And plug in this whole thing for Q of water and this whole thing for the Q of the metal. Now if I do that, I can solve because I only have one unknown variable. So let's do it. We have 320.5 grams times 4.184 joules grams degrees Celsius times T final minus 25 degrees Celsius is equal to negative 3 324.5 grams times 0.444 joules grams Celsius, and then times T final minus 100. I know I ran out of room there a little bit. All right, we'll move it over in a second. So the next bit is I'm going to take some numbers and combine some like terms. Okay, so as you can see here, I just basically took these two values and I multiplied them together to get that value. And now I'm going to do the same thing on the other side. Okay, so now I've taken, again, these two values and I've multiplied them together. That got me this value. And so now I have a workable solution here. I can either distribute into both of these two parentheses or just divide over and then distribute into one of them. It honestly doesn't make a difference. So let's do the second one. I'm going to divide both of these by negative 144.878. That'll cancel that. Sorry, 144. All right, and this will get me negative 9. Use the same notation I've been doing. Negative 9.307 times TF minus 25.0 degrees Celsius is equal to TF minus 100 degrees Celsius. And so now I can distribute in and rearrange and solve. So let's look at that over here. All right, so now the last step after doing this last little algebraic step is to get the TFs on one side and the temperatures without any variable next to them on the other side, and then we can divide and solve. So let's do that. So what we get is I'm gonna add 100 to both sides and add 9.307 TF to both sides. And I know this is getting messy, but what I get here now is going to be 332.7 is equal to 10.307 TF. And so I can now divide both sides to get my T final, which will be equal to about 32.3 degrees Celsius. All right, so that is a little bit more of a complex problem. The algebra is definitely a little bit more messy than the previous problem, but still pretty doable. One of the things to kind of think about here is because of our initial temperatures that we had, 100 starting for the iron and 25 for the water, we know that the final temperature has to be somewhere in between these two values, right? Because if you added cold water to a hot piece of iron and its temperature went up, that would be weird. Or if you had hot metal to cold water and the temperature went down, that would be crazy. It would never happen, right? So the temperature of the water is definitely going to go up. The temperature of the iron is definitely going to go down. We're going to meet somewhere in between these two values. And as you can see, that's what we had happen, right? Our 32.3 degrees Celsius is in between 25 degrees Celsius and 100 degrees Celsius. All right, so as always, if you have any questions about problems like this, please let me know. I have office hours, or you can set up an individual Zoom meeting with me, and I'm happy to do that whenever you can meet.